Alright, welcome back. MECH2320, control transformer. This is our topic for chapter 6. Alright, moving right along. As we go through this, alright, you want to be able to, kind of understand the use of a controls transformer and why we have one. And you're going to connect actually a control transformer in your labs and things like that. So, in the control, in the industry, the control transformers, most of them operate anywhere from 240 up to 480 volts when we use them. Usually we use magnetic controls if we have a 120 volt system. So we're going to take a look and see what we go through here. Now normally we have transformers that either step up or step down. So remember, we spent a whole chapter on this in the electrical class in MECH2320. So it's going to be based on the primary windings, and it depends on what we need. Do we need to step up the voltage or do we need to step down the voltage? It just depends on what we're trying to run and what the output's going to be. Okay, so if we take a look at this and we look at a transformer, we're using it to step up. So remember, we talked about turns ratio and all those good things when we did this calculation. Okay, how the number of turns on the primary affected the number of turns on the secondary. And the relationship was always secondary or primary for the ratio, okay, and how we use that to know if it was a step up or a step down. So essentially, if we had something like a 4-to-1 ratio, it means that we'd have, for every 1 turn on the primary, we would have 4 turns on the secondary. Okay, so that's how we would take that approach and understanding. So if we want to step down. So this is a step-down transformer, this particular example. All right, we connect the primary windings. Primary, remember, is always shown on the left. So we're going to connect the primary windings in parallel to one another. Okay, so when we connect them in parallel, and if we look at this, remember this is an iron core transformer because we have the 2 double bars. So when we go in parallel, we are going to get a step-down transformer. This will make sense in a few slides. Why we're in parallel, because remember when we had transformers, we talked about different taps. We could do a center tap or those sort of things to get the voltage that we want. So it makes sense here when we kind of look at the big picture on one of these here in a few minutes. So when we make that connection, okay, so we can kind of see the whole relationship here. We look at the bottom, kind of schematic on it, how H1 and H3, okay, where that node is and how we connect those nodes. Okay, so we can use some metal linkage to get across those windings. Okay, and based on how we make that connection, our output is a step down transformer, okay, and we'll get 120 volts AC out of it. The same kind of concept here when we step down into your neighborhood. All right, remember we talk about transmission lines and those sort of things, and we can use the 240 a couple different ways. It can be either, we can do it in parallel as such to step down to 120, or we can do a split voltage. Alright, so we can add those up and center tap and do that as well. So, because that's how you would use it in your house for your dryer or those sort of things. So we could do a split tap and get 120 as well. Okay. So remember though, it's based on the windings if we're a step down or step up transformer, based on the windings of the primary and secondary and how that relationship is with the ratios. Alright, so if we want to step 480 volts down to 120 volts, okay, we're going to put it into series. So just kind of remember the difference here, because it's going to be based on voltages and how we want to get the desired voltage in this case. Still, notice that these transformers are wired in series, and it's going to be where we put the tap, all right, for the to get the 120 volts out of it as we're doing that calculation. So same kind of concept here. We're using a metal linkage to connect those. All right. Hey, remember transformers work on induction as well. So it's the coils of wire around the iron core conductor, and remember that those connections don't actually meet on the primary and the secondary, don't actually connect physically. Everything is induced with a magnetic field. Alright, so then they make that series connection using the metal link on there. So we have multi-tap transformers, okay? And these are fairly common, all right? And you'll see one of these in the lab. So we can sit here and, based on how we make our specific connections, that's going to get us our output for 120. So regardless on this transformer, our output's always going to be 120. Do you see that? The way this would be set up, X1 and X2, always 120. It just depends on what our line is coming in, where we need to wire to, whether we got to wire to H1 and H2, H1 and H3, or H1 and H4, based on what our input voltage is that's coming in. Okay? We use some smaller transformers as well on a few of the other trainers that you're going to use, like the Untitled trainer. You're going to bring in 120 volts, and then we got to rectify it, and that's actually going to control our DC power, so we get 24 volt controls as well. So same kind of concept here, just different voltages doing different things. So this is a multi-tap transformer, very, very common. All right, next part's understanding how to make your measurement readings and understanding that sort of thing. So you'll be doing this in your lab as well, all right, but you're going to use a multimeter for this. And we're going to use the voltimeter to check our voltages and make sure that everything's working properly. But it does depend on the grounding point to come up with our test voltage, all right? So very important here that we understand a few concepts of how to do this, okay? So one basic setup, and most of this is already done in the industry, one side of the control transformer is wired to ground, okay? So that way that we can actually take readings on it. Since it is tied to ground, that allows us to take readings and connect to anywhere. As long as the transformer is grounded on one side, we can connect to a grounded point anywhere else and get an accurate voltage reading, okay? To make sure, if we need 480 volts across the line there, that we're reading 480 volts as required. But, common industry practice doesn't always ground the control transformer. So notice in the schematic here, it's not grounded. So what this does for us though is this is a meaningless voltage because it's not in the same system. So that grounded point, since that control transformer doesn't go to the same ground as what you're using for reference here, okay, our voltage, we call them like ghost readings. They're not necessarily real readings, nor accurate whatsoever, because it's not on the same system essentially. So we call this float grounds when we make this kind of connection. But for us in industry here, it's not necessarily going to give us an accurate reading because the control transformer is not grounded. Okay, the best way for us to get an accurate reading here is to read as we are here, from the motor to the ground side of the control transformer. Even though this transformer is not grounded here, all right, it's just the neutral side that's completing the path. So you would have to make this reading across the motor to get the accurate voltage drop. So hopefully that you understand the difference. We do not I'm going to back up a slide here. We do not use this method to read the voltage across the motor or anything. Okay, it's a float system. It gives us ghost voltages. So the only two ways that we can read this method only works, I'm going to step back a slide here again, is if the control transformer is grounded. Notice on the schematic there's a ground symbol there by the control transformer. This method works. So if the control transformer is grounded as such, we can use the voltmeter here to take a reading because the ground point and ground there mean the same thing. In this case, right, we're not grounded. This is a float. We're getting ghost readings. This, we're reading the voltage drop across the motor accurately, just like we do when we breadboard. So this is the most accurate reading for us. This is the most common one, all right? Industry-wise, most common, we're not grounding the transformer, but if we can read across the transformer, because remember, using your voltmeter, you always read across the equipment anyways when it's energized. Okay, we can also, protect the transformer. We protect everything, whether it's with the breaker, overload relays, all those different things. So you'll notice when you open some, a control panel up or things like that, the transformer will also have fuses on it. And this is much more practice on the larger voltages and things like that. But you'll see that there's a fuse for each line. Okay, they're placed on either the primary or the secondary. side of the transformer. You don't put them on both sides because it's kind of insignificant there, right? Or it's redundant, essentially. But you'll have them on one side. So if you get more into this in industry and things like that, you're going to have to actually look everything up. So the NEC code, which we've mentioned multiple times, if you open up to that specific section, it tells you the requirements for the protection of transformers. And because transformers come in multiple sizes, multiple taps, step up, step down. So you're going to have to look at your specific transformer to understand what the specs are and how you need to protect it. Okay, so and then lastly, since they do have a fuse, you can see that the fuse shows up on the schematic and where it is. In this case, what side is the fuse on? Is it on the primary side or the secondary side? Okay, so for us it's the secondary side because we're on the controls. Okay, let me break this down to the big picture for you before we wrap things up here. If you look at line 1, line 2, and line 3, that's the main power going to the motor so that the motor runs. Okay? And we've talked about the motor contacts, we've talked about the overload relays, we're taking a look at the schematic. Gradually, you need to understand everything that's on these schematics as we go through them. Notice that the control transformer taps into the main power that also feeds the motor. So that's why I was saying before, it depends on the voltage coming into that control transformer. So we need leg 1 and leg 2. You're not sending 3 legs of power in there. That control transformer dummies everything down into our 24 volt potentially, or whatever our control voltage is that we're using there. So we obviously protect it with the fuse. Okay, we have a push button there. That's what our stop button. Okay. Then we go over, we have a push button that's a start button, and it's in parallel with our motor contactor. Okay, so everything on the bottom of the schematic is your controls. So pushing that button manually starts the motor, right? We've already talked about manual switches. That motor, that circle with an M around it, okay, that's our motor coil, okay, contactor. That's not the official motor. The motor's at the top, all right, of the schematic here on the diagram. So that's our motor coil. So when we press the button, okay, the motor coil energizes as long as the stop button is not pushed open and as long as we're getting power to the transformer. Notice the overload relay contactors are all in series with each other, and each one of those overload relay contactors applies to each line that's feeding the motor up above. And then we have the seal-in logic, right? We talk about this in the PLC class. We have our seal-in logic, all right, so that the motor stays in operation until it's stopped, either with shutting off the contactor with the PLC or pushing the stop button. In this case, all right, this is more manual. This is not automatic with anything else. You'll see as we go forward where the controls lie. And this isn't necessarily a complete diagram, but I kind of want you to start seeing how everything is pieced together. Okay, notice the push button on the bottom part of the schematic here, the push button that's tied to contactor M. That M is the same contactor that's at the top of the schematic that's normally open for line 1, line 2, and line 3. Because when you push that button, you're closing all 3 contactors at once. All right, so that applies to the last lecture where we talked about those sort of things. Alright, so hopefully all this is starting together to come together here, and we can see where and how the control transformer is used. Main power coming in, and then we step it down. Because remember, we don't use high voltage for controls. We use low voltage for controls. We use high voltage to run our motors and machinery and equipment that need it, alright, so that they can work through and handle higher loads. Alright guys, well that wraps up this lecture. As usual, contact me if you need anything else. I'll see you in class and have a great day.